Okay, anybody else turning in the assignment from last time? It's going to be the last call here. Okay. All right. So I want to pick up where we left off. We're trying to find the assignment that I asked you to do at home. What's wrong, Luke? These guys, y'all aren't friends anymore? Okay. All right, that's okay. I asked you to find the parametric equation, the vector equation of the surface, this front face up here that has a tilt to it. So let me remind you of what we did last time. And specifically, when we found the parametric equations for the surface, the bottom of this thing, right? What we did is we said, okay, if you look at that bottom piece just in the xy plane, we know that since it's on the ground, the z component of our vector function will be 0, right? That'll keep it flat. And then this looked a lot like a type 1 region back from double integrals, with the exception that we're going to switch x to u and switch y to v. And then notice that if we let x vary, right, between 0 and 3, if we pick some arbitrary, u, if we let u vary between 0 and 3, then we want our v to actually be everything in here, right? So it would draw that entire line segment. And to do that, what we did was we let v in the equation just be v, and we restricted it between 0 and the line in order to let v go up and down, right? And that created the sheet that we needed. Well, the only difference between this and this plane that comes in at an angle is that, like, if you looked at it straight from the top, right, it would look exactly the same, wouldn't it? The only difference is the z is different. Now, I thought this might be a good time to remind you, back when we were doing triple integrals, our regions of integration were three-dimensional, right? Solids. If you were to define this tetrahedron as a triple integral, you would say my x's are between 0 and 3, right? My y's are between 0 and this line, right here. And then my z's are between 0 and, which is the ground, and what? The plane equation, right? Solve for z, that's what this is. But that would make the solid, wouldn't it? Because your z is everything in between 0 and that plane. What we want for our vector function is to not have every z between this plane and down to the ground. We just want the one on the plane, right? So the only difference is that this right here needs to live on the plane. And so what you had to do at home, I'm going to have some trouble talking today. I'm getting over something, allergies. My throat's real itchy. You had to find the plane equation, so that's where you took two vectors on there and crossed them and got your normal. Okay. So the plane equation, what I got was this, 8x plus 6y plus 12z equals 24. I believe that's what I got, and you can reduce that out. And if you solve that for z, should I just reduce everything by a factor of 3 right now, or a factor of 2? Sure. You get 4x plus 3y plus 4z equals, what's that, 8? And then you solve for z. What's what? Yeah, sorry. Sorry. I don't know what I'm doing. And then solve that for z, right? Okay. Man, maybe I should start this whole day over. That's how I felt. This is how I felt all day. What I'm doing up here. All right, so here I'm going to solve this for z and replace x and y with u and v, right? So I got, I left it as like this, 12 minus 4u minus 3v over 6. And of course you could split that up and do 12 over 6 is 2 and then fractions. So what's really important for you to understand here is that this is only going to give you a single value for the z. Once you pick your u, right, your v's are stuck between two numbers now, and everything in between those two numbers is going to get plugged in here. And so what's going to happen, I'm trying to draw it for you. You pick a u, which is like the x. You pick a u, then it draws, your v's are restricted between here and here, aren't they? That would be like this line was. And then everything on that line gets plugged into this, which would give you something like, just those points up into the plane would give you that line segment on the plane. And if you do that for every u value, right, pick another u, every point here up into the plane, then eventually you draw the whole plane. Understand? Okay. We're going to move on. We're going to finish up this worksheet. So hopefully anyone need one? I think I have an extra. You have like $2 or something? Yeah? Okay. Did anybody try and do the other ones? No? All right, so here it is. You have part of a cylinder, all right? And it's hard to tell from the picture, so I'll turn it to the side. Can you all tell what the restrictions are here on our y coordinate? I think it's 1. I think it's a 1 to 4. Look, see that? 1 to 4. Okay. And then can you tell what the radius of this cylinder is? Can you all tell? 1. Can you all tell? All right. So we need to come up with the parametric equation, the vector formula that would draw that surface. So any ideas? I need it to be r of uv, right? I need 3 components. Okay, so you have a bunch of circles, don't you? And so you could just start by trying to draw just one circle, like this outer edge. If I try and draw that outer edge, that is a circle in which plane? Parallel to which plane? The xz plane, right? Understand? So how we would draw a circle in the xz plane, and it's a unit circle, is to use the whole r cosine theta, r sine theta thing, with r being fixed here at 1. Yes? But instead of using theta, I need to use u or v, so it's your choice. There's no like accepted convention that we always use or anything like that. So what do you want? U or v? U? Okay, so in the x component, I'm going to put cosine u. In the z component, sine u. Everyone agrees that draws a unit circle that would be parallel to the xz plane. Yeah? Then I just need to take that and move that circle back and forth, changing the y coordinate between where? 1 and 4, right? So like if I just put 1 here, that would draw me this back edge, wouldn't it? If I put a 4 here, it would draw me this front edge. But I want everything in between. So if I'm going to need that to vary, I'm going to have to put a variable here, right? But I can't use u, so I'm going to use v. And then I'll let my u go between 0 and 2 pi. That'll draw me circles. I'll let my v go between 1 and 4, and that will move those circles back and forth, and that'll give me the cylinder. That's not so bad, right? Questions? What is the difference between that and this equation? My parametric equation that I just gave you and this, what's the difference? That goes forever in each direction, right? And there's no easy way for you to tell me how to control this, right, if I want that, unless you actually explicitly say, you know, y is between 1 and 4. Then they would draw the same thing, wouldn't they? Just want you to understand that this equation right here is not the same as what we just came up with. This is actually more than what we wanted. Okay, now this one. Find the vector function r of uv which yields the red end cap of the cylinder shown here. So it's the same cylinder we just drew, okay? But I want this red end cap instead of the blue. So what's the difference here? Not the back, just the front. I just want this front piece. What? Two. Yeah, see, look, when we drew the cylinder, it was the same circle the whole time, right? Right? And it just moved it back and forth between 1 and 4. Here, we don't want the same circle. We want a bunch of circles from radius 1 all the way down to a point, and we don't want to move it back and forth, which is good because we needed a variable to move it back and forth, didn't we? Yeah. So I think it should look very similar to what we just had in terms of the fact that we can use cosine in sine. That draws circles. But this time we'll have a varying radius. So how about we use cosine u, sine u again. That will draw me circles in the xz plane, but I don't want unit circles, right? Something you can control. So how about we use that other variable v here? V times this. V times this. Now what about the y? That's going to have to be 4. If I'm going to be this front end cap, right? That's going to be 4. What if I wanted the back end cap? It would just be a 1, right? What if I wanted to draw the whole solid? Well, I can't use these, okay? These only draw surfaces. Now, you could introduce a third variable, but we're not going to. You could, though, and that would solve the problem somewhat. All right, so this is it. What are my restrictions on u? 0 to pi. And v, I want these represent the radius, right? Or the radii of the circles. I want them to go all the way down to a single point, 0, all the way out to 1. Any questions? Sure? Everyone understand the fundamental difference between those two problems? All right. Let's look at the next one. All right, I tried to give you as much information as I could on this one, on your picture, but let's look at it from the side. It touches the xz plane. You see that? Yeah, can you all see that? Touches the xz plane. And this cylinder, if we look at it from this side like this, the cylinder has a radius of what? 1 again. And then it gets sliced. So what did I write on yours? Hold on. Okay. I put y equals 0 on the back side like this. Y equals 0. I put what? Z equals what? And then anything else? And then the cylinder is the same as the one before, right? So you could, if we wanted to, label this one x squared plus z squared equals 1, right? Understand? Yes. So what we want in this problem is to find the vector function which yields the three surfaces shown. That means we're going to have to come up with three different vector functions. We can't draw them all at the same time. We have to just do one at a time. All right? So let's label these. Why don't we call this one over here the backside? Okay, why don't we call that backside S1? Why don't we call this one over here S2? And the one that comes from here S3. Does everyone understand that this is a cylinder that's been cut with the plane y equals 0 at the back, like this, cutting it at the back, and then cutting it with the plane at an angle that cuts it off this way. And that's the plane that we use to cut it at this angle. Got it? So we have three surfaces. Let's start with S1 because it's probably the easiest one. All right, S1 looks exactly like the one we just did. I'm going to call this R sub 1, so everyone knows which one I'm talking about, of uv. And this should be v cosine u, 0 v sine u, and u's between 0 and 2 pi, v's between 0 and 1, right? That should draw me the backside. Now is the question of which one do you want to go after next? S2 seems natural because that's the way I labeled it, but I think S3 is easier to see. Okay, on easiness, yes. So what is the difference? What's the only difference? That's a hint. What's the only difference between S1 and S3? If you looked at them from the end, if you were standing here on the y-axis way down there, and you were to look at them, could you tell any difference between S1 and S3? No, I'm never going to get this back where I want it. Oh, damn. Okay, I guess I am. Okay. They look exactly the same, right? Because the only difference between them is the y-coordinate, right? You can't tell that it's coming out, like this one is actually coming out at you, where that one's laying flat. So the only difference between S1 and S3 is this y value. You still have to draw everything. This is like a disk, right? Almost. It's not a disk, but you still have to draw everything on the inside of it, okay? But what can you tell me about that y, the y value on that S3? It has to follow this equation, doesn't it? Because it has to live on the plane. Understand? So since I know this is the only difference, I come in here and I look at this equation and I solve it for y. Because that's the part I'm interested in. Solve this equation for y, and what would you get? Y is equal to z minus x plus 2, right? So let me write this down. S sub 3 is r sub 3 of uv. And this should be equal to, I know that my x component must be this. My z component must be this. Right? That's still giving me that disk effect, right? The y part, the part that's coming out at me, though, is going to change depending on my x and on my z. And it will be exactly my z coordinate minus my x coordinate plus 2. But what's my z coordinate? V sine u. Minus what's my x coordinate? V cosine u plus 2. So right in here, I'm going to need a little more space. This should be v cosine u, that's the x. The y is z, v sine u, minus x, v cosine u, plus 2. And then v sine u. Do you all see that? To determine my y coordinate, right, I have to refer back to my x and to my z to get my y. So this is the x, this is the z. What about the restrictions? Same exact restrictions. Okay. All right, we good?
So how come, well, I mean, I understand the U, but how come the restriction on V is the same as the first one?
Again, it goes back to the idea of if you were to look at it from here, what's happening in the XY plane, XZ plane is exactly what was happening with this one in the XZ plane.
It just happens to vary, okay.
Right? Imagine this. Imagine I draw this circle right here. Okay? That has a certain radius to it, right? You don't know, you can't tell by looking at it straight this way, you can't tell if this point and this point, you can't tell if those are the same distance from you. All right? Right? It's only the y coordinate would tell you that. So if I twist this back to where it was, right? And now let me draw that circle on there for you. It would have really looked more like this. That circle would have looked more like that, right? Now you can see one of those was closer to you than the other one. But the only thing that made that happen was this. Okay? So everything else follows the same exact formula, which is actually nice that that works that way. We good? Any other questions? Okay, what about S2? So what about S2?
It's a cylinder, but you're cutting it between two planes.
Yeah, it's a cylinder between two planes. So how do I draw a cylinder with that fixed radius? Right, because the radius of this is always 1. So again, if we turn it and we look at it straight through, whenever it does draw something, it draws a circle of radius 1, right? It has to be lying on a circle of radius 1. So the radius is no longer varying. Agreed?
Right.
Okay, so I'm going to put S3 here, or S2 here. So what are you suggesting? Cosine U. The Z being sine U. This is the hardest part right here. This is the hardest part.
Can you do V and set the 0 to the equation?
Exactly, perfect. That's the way we do it. We don't try and control our y coordinate in here. We want to control our y coordinate in the inequality restriction. Now here's why. Let's say this is going to draw me a circle, right? So imagine drawing the back circle like this. I kind of missed it there. What I'm going to do is I'm going to draw that back circle, and let's just say I'm drawing this point right here. That's somewhere on that circle, right? What I want is after I've drawn that point, I want my y coordinate to be able to vary back and forth between there and there. And if I pick another point over here, I want it to go here to here. Now remember, this is the front edge, right? It's really hard to see this. I think I messed that up, but that's the edge, right? So as I pick points along that circle, I pick the point, I fix the point, which would be, I plug in one of these u's, right? Any u between 0 and 2 pi, plug that u in, I've got a point on that circle. Then I want my y coordinate to go back and forth, so I'm going to let it just be v. And that v has to be stuck between what two y values? 0 is the back, and the front y value is this plane right here. Yes? So I'm going to let v be stuck between 0 and, again, this is the trickier part, z minus x plus 2. but we have to use these, right? So what's z? Sine u minus x, which is cosine u, plus 2. Got it? Can anyone tell me what would have happened if you would have instead put this right here? What it would have drawn? Basically, take v out of the problem, because that's what you would be doing, right? Take v away and just put that right there. What would it have drawn? Not quite. Which curve? Which curve is what I'm saying? Which of those curves would it be? It would be that, it looks like an ellipse, right? It would be this curve right here. See, because what you're doing is you're drawing a circle, but you're making your y-coordinate be out here on that plane, instead of letting it vary between 0 and the plane, which is the way we had it, which is the correct way. Understand that difference? Okay, so forget this. Don't want to do that. Don't want to do that. Do we have all the surfaces? Yep, okay, we move on. Our goal here is today is to try to get to 13.7. We'll see if we can. We haven't even started 13.6. I mean, this is just the introduction to it. All right, so what about this? Find the vector functions which yield the two surfaces shown here. So we have a bottom cap and then this little cover, right? So what do you want to start with? The circle on the bottom, that disk. Okay, what about that disk? Okay, so why don't we call this one S2? The one on the bottom there, we'll call it S1. S1 will be the vector function. What for sure? What for sure here? 0, 0, okay, because it's on the ground. All right. And then the other part, it's a disk, which is a bunch of different circles with different radii. So v cosine u, v sine u. Are y'all catching on to this? Y'all getting this? What's your restriction on u? 0 to pi. Good. Restriction on v? 0 to 1. Now you can tell it's 0 to 1, can't you? But in the event that you were not able to tell, you could also find where this surface here intersects the xy plane, which would be setting this equal to 0, which would be a unit circle, right? So it would be 0 to 1. Okay, any questions there? All right, what about S2? What's the main difference between S2 and S1? The z's not fixed anymore, right? Everything else is the same? I mean, other than the z? Right, if I look at that from the top, I can't tell the difference between those two, right? It's just the z that's coming out at me is the part that's different. So this should stay the same. But my z needs to be what? One minus this squared minus, sorry, minus this squared minus this squared. Minus v squared cosine squared. We're going to wind up doing Pythagorean, right? So factor out of negative v squared. The cosine squared plus sine squared will become 1. So this is really just 1 minus v squared. Yes.
Do you have to have the V though? Because if you're just going to draw the circle on the bottom,
Where? On which one?
on the surface 2,
Uh-huh.
for the X, Y coordinates,
Uh-huh.
do you have to have the V? Because if you just draw the circles, isn't it going to eventually draw all the circles to the top?
They won't be varying in radius,
Oh, that's right.
right? You want to circle. See, and this is the thing when you let V be 1, right? I'm sorry. Let's let V be 0. When V is 0, where are we? 0, 0, 1. We're up here, right? Let's let V be 1, which is a radius of 1. We'll be at 1, right? 1, and then over here we'll be at 0, right? But this will be cosine u, sine u, 0, which is a circle, unit circle, z coordinate 0, which draws me the bottom. Like this, right? Then if I let v be a half, I'm going to get a smaller radius, and then this is actually going to be 1 minus a fourth, 3/4. So I'll be up here drawing that circle. Does that make sense? So you've got to have that v to vary the radius as you move up and down. We good? Okay. I think there's one more, right? Okay. So I told you the back side of this, y is 0. This right here, z equals 1 minus x squared. This right here, x plus z equals 2. And then, of course, the bottom of this, z equals 0, which means it's flat on the ground. I didn't do this one. Okay. All right, so where do you want to start? Let's do the bottom. Okay, let's label these. I'll just go clockwise. S1, S2, S3, S4. So for S1, this is R1 of UV. This is just a what? That bottom there? The bottom piece? Just a rectangle, right? It's just a rectangle? That's as clean as you're ever going to get. What can you tell me about the z coordinate? It's 0, okay. And then how about I just call the u coordinate u and the y coordinate, sorry, the x coordinate u and the y coordinate v. And then just go between two constants, right? U's between what? -1 and 1. Do y'all see that? That's my x values are between -1 and 1. My y values should be, so v should be 0 to 2. That's pretty clean, right? All right. What do you think is the next easiest? That S2, right? All right, so let's talk about S2. I'm going to draw S2 in the XZ plane. It's that whole surface, right? That's what it is? Is that shape following, what function is this following right here? The parabola what? Z equals 1 minus x squared. It's coming from this thing, right? Anything that you can tell me straight away from this that's going to be nice? The y coordinate is 0, right? That's fixed. Now you have two variables that you have control over here, right? Let's switch our x to be the u. So I'm going to let my x vary, right? So I'm going to let my u vary between where and where? -1 and 1. What about my z coordinate? What am I going to put here? What's that? Z and there's, let's use V, but yes. We're going to switch our X to U. We're going to switch our Z to V. And I'm going to call this V, and then let V be between, where? 0 and the curve, right? It'll draw me everything in between. So between 0 and 1 minus x squared, but for us, u squared. Understand that? Again, let me ask you one time again. If I put 1 minus u squared here, then you wouldn't have a v, and what would that have drawn? Just the curve, right? All right, I'm good with that. What do you want to do next? Let's take a vote. S3? S4? I'm for S4. The reason why I'm for S4 is only because it's almost exactly the same as S2, right? The only difference is, again, if we looked at it from down here, we wouldn't see a difference between S2 and S4, would we? The only difference would be the y coordinates coming out at us. It's changing. So the y is somehow going to be variable when we try and do S4. So S4 will be u. This will be v still. But what about the y coordinate? It's fixed, right? The y coordinate is fixed. So the way you can think about it is if we're going to use the same restrictions here, that's going to draw this, right? So I pick some u value. It's going to spit out some v value, which is really the z. But I don't want to be flat. Where do I want to be? So like I'm right here on that backside right now. I want it to come out and actually be that point instead, right? Not everything in between, just that point. So I need to move that y coordinate out to this plane. What's this plane equation? Wait a minute, is that right? Hold on a second. Did I write that down right? Ooh. That needs to have what in there? A y. Hold on a second. We need, do y'all see, hold on, let me look at my code here. Where did I draw that plane? Which one is it? That's supposed to say y plus z. My apologies. Y plus z. Do y'all see where I ran? Like I was sitting there going, oh shit. Do y'all understand why I was saying oh shit? Okay, because this plane equation right here, please change. That plane equation, I need to be able to solve it for the variable that I'm trying to get some control over, right? So this right here, we're trying to control the y. If I solve for y is equal to 2 minus z, right? Do y'all see that? So if you're going to live on this plane, you've got to have the equation 2 minus z to live there. And I know the z coordinate, don't I? The z coordinate is my v coordinate. So this should be 2 minus v. And then same restrictions as we had here. Is that okay? We're not done, but is that all right with you?
Yeah.
All right. For those of you who again like the code, I know no one. I keep on saying for those of you who like the code, no one has ever told me, yeah, I really like the code. This is basically what I'm doing here. Parametric plot 3D is a function that's built into this system. So I'm calling on the function parametric. This is a parametric equation, right? These are parametric equations. So I need to give it the x component, y component, and z component. So I gave it u, v, and then this is 2 minus v, which is exactly what we have. I let u vary between -1 and 1. I let v vary between 1 and 1 minus u, between 0 and 1 minus u squared. And then I tell it to plot it so that it's somewhat see-through. Okay, opacity 0.4 means that it's transparent. Opacity 1 means it's not transparent. Opacity 0 means you don't even see it. You just see the boundary of it. And then make it red. And then I tell it about how to draw the axes and things like that and how to label them. But
you said this is based off C++, right?
it is, but it's C++ basic language here. But imagine just a bunch of built-in functions. When I first started coding in Mathematica, a lot of it was like more C. You had to code. Now there's so many built-in functions, that all I do is bring up this thing called a palette, and I can call on all these different functions. Like if you want to do, there's pretty much anything is here. If you want to integrate, where's the algebra one? Simplify, expand, factor. It goes on. So really, I'm not coding as much as I understand the syntax, but a lot of it is just pulling on other subroutines. All right, well, we're left with one more, right? S3. So for S3, the difference between S3 and S4 and S2 is that it's just the edge, right? Just the edge. So I don't have to fill the inside, and that's good. That should free up a variable. And I can use that other variable to control the back and forth. So what do you think? You help me out here. S3. Draw me the boundary without any care at all right now about the y coordinate, back and forth. Draw me the boundary. How are you going to draw me the boundary? X is u, and what's that? Z is v. Look. You want to draw it, look, this is it, right? This is the xz plane. So I'm looking at that from here. I'm trying to draw just the blue. The blue is going to lie on here, right? But not the inside. So it's got to follow this equation right there. 1 minus u squared, because u is our x. You see that? You see that's a big difference here. Because here our v, we varied it between 0 and this, which drew everything in between. When I don't use v here and I fix it, it's just going to draw that edge. We need that because we need the v for this part, for the back and forth. So now I'm fixing a point on this edge. Once I fix a point, I need to vary back and forth between here and here. And that's between where and where? Y equals 0 and 2 minus z, right? Which for us is something else, right? So what do I call this? V. Let this be the thing that you're going to control down here. U's between where and where? -1 to 1. V must be between 0 and this plane, which is 2 minus z, but z for us is this. So 2 minus 1 minus u squared, which is really 2, not 2, which is really 1 plus u squared. Understand that? So?
No, yeah, I got it. I was just,
I'm going to draw one point for you. You give me a, let's take a test point. If I let u be 0 right now, right? If u is 0, then I'm right here on the, it's like x being 0, right? What's my z coordinate going to be? If u is 0, what's my z? 1. So I'm 0. I go up to 1 on my z. Now, what is my y coordinate going to do? It's going to be v, and v is going to be between 0 and 1 plus u squared. But what was u? It was 0, so it's going to be between 0 and 1. 0 and 1. There we go. It's going to draw me all those points. Okay? Let's do another one. What if u is 1? Where am I going to be? If u is 1, I'll go out 1. What's my z? 0, so I'm here. And then I'm going to let my y be between, my v, which is my y, goes between 0 and 1 plus 1 squared is 2. So 0 all the way out to 2 gives me that. Does that make sense what's happening here? I'll take one more just for fun. If I take 1/2, that's here. 1/2 right here, I go up what? 3/4, which is there. And then 0 to, what, 1/2? 1 plus 1/4, right? Which is this, which is further than this one, right? That one was 1, this one's 1 1/4. All the way down here was 2. Understand? All right, that is the essentials for parametric surfaces. We will need this not so much in this section as much as we will in the next section. All right, 13.7. Oh, there was one more thing I wanted to show you. It's related to this, but it's not in the notes. Everybody knows the equation of a plane, right? Equation of a plane. A, x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0, where a, b, c is a normal vector and x naught, y naught, z naught is any point on the plane, right? We're all familiar with this. Okay, we have another way that you can come up with the equation of the plane. This is the vector form of equation of plane. Now, recall this formula. Remember that? That was the vector equation of a what? Line. This is a line, right? And what happened basically is that we said, give me a point on the line, and give me a direction vector, and then give me all scalar multiples of that direction vector, and I'll draw every vector in that direction and in this direction, and it'll create the entire line. Right? Basically, that's it in a nutshell. We're going to now do the same thing for a plane, but here's the difference. Plane is going to have, a line is really have one direction. For a plane, we're going to need two directions. So somebody give me a point, right? Start with a point. Give me a direction vector, not the normal vector. Give me a direction vector. This vector needs to live on the plane. So let's use this wall as an example of a plane. I pick a point on it, take a vector on that plane. take another vector on that plane, like this. If I take every multiple of this vector and just don't even care about this, it'll draw this line, won't it? Now, what if I add this vector to every one of those? Then I'll have another line that's parallel to this, won't I? Oops, like that. What if I take this, every one of these vectors on the, parallel to this line, and I add half of this one? I'll have another line going in each direction like that. And if I do that for every multiple of this line, then I'm going to create the entire plane, aren't I? But you could also do it by saying, take this vector and this vector, add them together, parallelogram rule, you'll get this vector. And then you do two of these vectors. Parallelogram rule, you'll get that vector. Do three of these, parallelogram rule. Do every multiple of this with every multiple of this, and you get the whole plane. All right? So what our equation turns out to be for the vector equation of a plane, it's going to still require a base point. I'm going to use u and v because it's a surface, right? So it's got to have u and v in it. I start with the base point, base vector point. I add to it every multiple of some direction vector. So I'm going to say u times the vector, I'm just going to make it up, a, plus v times the vector b. Do y'all see that this is the same formula as this? Take this out, and this is r naught plus the t is now u, and the v is now a. But now I'm adding a separate vector, a different vector, and all the multiples of it. So what we're doing is we're taking every linear combination of these two vectors, which is called the span of those two vectors, which in this case would be a plane. As long as these vectors are not parallel. If they're parallel, then you won't get a plane. You'll get a line. But okay? I just want you to be familiar with that, just like you've seen it before. All right? There is a way to draw a plane with two vectors. It just requires two vectors on the plane. Now we can get into 13.6. 13.6, yes. Parametric surfaces and their areas. All right, what we just learned a minute ago in the last class, ignore that please, is that if we have a vector function r of u v, that this will draw us a surface in three-dimensional space, right? That's what we took time practicing, trying to come up with the formulas for these surfaces. One example of a parametric surface that you don't quite remember as being a parametric surface was when we did spherical coordinates. Do you remember when we did spherical coordinates? We switched over, we let x equal rho, sine, theta, cosine, phi, all that junk. We had three variables, didn't we? Rho, theta, and phi. If we fix rho, right? If we fix rho, that was the radius of the sphere, then we only have two variables. So look at this example right here. If I take my r of u v to be sine u cosine v, sine u sine v, cosine u, then, hold on a second. Ooh, yeah, the u is like the phi, just so everyone knows here. The u is like the phi was, and the v is like the theta was when we used polar. Okay? Then if I look at, where's my picture? There it is. Where is it? Hold constant. I want to hold the v constant. So if I hold my v as a constant and let my u change, I'm going to draw these little semicircles. If I hold my u constant and let my v change, I'm going to get all these circles in the other direction. And if I put all these together, I get all these grid lines together, and it creates the sphere. All right? So now let's talk about derivatives. If you have a vector function, back when we were drawing curves, then the derivative of that vector function was a vector that was tangent, right? Tangent to the curve. As a reminder, it looked like this. Here's a curve, and then we move this thing around. That red vector there was r prime of t. And we know that we could extend that line, or the vector, out in each direction and create a line from it, right? Now, what does it mean to talk about the derivative of our vector function of two variables? Well, if we have two variables, then we can't take a derivative unless we hold one of them constant, like a partial derivative. So if you see this r subscript u, what it means is take the derivative of the vector function, treating your v like a constant. If you see r sub v, you take the derivative holding u as constant. But what does it mean geometrically? So here it is. If you hold, here's a point, right? If you hold one variable constant, you're going to get a derivative, and that's going to give you a vector, which would be something like this. If you hold the other variable constant, you get a different vector, which would be the one like this. Each one of those is tangent to the curves respectively, right? So this one right here is tangent to the green curve. This one right here is tangent to the red curve, right? Would you agree that both of those together, both those vectors together, live in a plane that is tangent to the surface? Yes? All right. And that's exactly what we have in this picture. So somehow the derivative, with the derivatives of these vector functions, we can come up with tangent planes to surfaces using this. This picture is just supposed to make you believe that that plane is tangent to that sphere. All right, so here's the first problem that we're going to do. Let's find the equation. Find the equation of the plane that is tangent to the unit sphere at this point. Any ideas? What's your idea?
Use that vector sine u cosine v.
Okay, so let's first let's draw the surface, right? We got to be able to draw the surface before we can find a tangent plane to it. How do we draw this surface? R of uv will be equal to, how did I have it written there? I think it was sine, I think I did sine, yeah, I just switched the order on accident there. Tell me if this is what I had up there on the previous note. Cosine u, is that what I had? Oh, those were both supposed to be different. I don't know why I didn't write that one. Okay, and the u was our phi, right? Which between 0 and pi. And our v was our restricted between 0 and 2 pi. So going back, if you go back to when we did spherical coordinates, this u was really the phi, and this one was the theta. All right? And also, our rho is 1. Why is our rho 1? Unit sphere. We okay? All right, if we do this, this draws us the unit sphere. We want to know the equation of the plane tangent to this sphere at that particular point. So what I'm going to need to know for the equation of plane is a point and a normal vector, right? I can get a normal vector on a plane if I have two vectors in the plane, and then I cross them to get the normal, right? Two vectors that live in that plane are going to come from the partial derivatives, because those partial derivatives give me tangent vectors, don't they? And each of those tangent vectors must lie in the plane. So I'm going to need from this to find the normal vector of the plane. I'm going to need to take the cross product of the two partial derivatives of r. Understand? That'll give me the normal. So let's go ahead and find the partials right now, and I'll come back and cross them. Well, maybe I'll do it all. See how bad these look. What's partial of r with respect to u? All right, with respect to u, cosine v, cosine u. Cosine v, cosine u. All right, partial with respect to u, cosine u, sine v. And finally, with respect to u, negative sine u. All right, that's not so bad. How about the partial with respect to v? Negative sine v, sine u. Then sine u cosine v. And finally, 0, because I don't have a v in the last one. Understand what's happening? So I'm just doing partials to each component function. Now cross them. Ru cross Rv equals, it's a vector, isn't it? I cover up these, and I do my cross here. Oh, that's nice. I get what? 0 and then minus negative this, right? But this, so negative, so it'll be plus, right? This times this, so I'm getting what? Sine squared u cosine v. That's it. Then cover up this one. 0, and then minus is plus, but then it's subtracted, but then it's negative. So what the hell? So forget that these are both negative. It's a positive, right? But I'm subtracting it because this is the second thing, but then I make it negative because it's the middle. So it's going to be a positive. Positive what? Sine v sine squared u. Okay.
Multiplying together, so it becomes positive, but you're subtracting it, so it's negative. But remember, the middle one will always switch.
But the middle one's always opposite, right? Yeah. Yeah. I know. All right. Last one. Oh, this one's kind of sucky. Cosine squared v sine u cosine u? Cosine squared v cosine u sine u. That's this times this. Minus, but then it's negative, so plus, I'm out of room here, I'm going to put it right here, plus sine squared v cosine u sine u. close the vector off. Anybody see anything? Nice?
Pull out the cosine.
Yeah, right here in this last component function, I've got a cosine u sine u, a cosine u sine u. If you pull that out, you're left with cosine squared v plus sine squared v, which is 1. So this last component is really just cosine u sine u, right? So I'll put this over here. My normal vector is going to be sine squared u cosine v, sine v sine squared u, and then cosine u sine u. That's what a normal vector will look like. You all good? Now, at this particular point, what's going on? So I'm trying to come up with the equation of the plane, right? Here's what I have so far. I know it looks like this. A, x minus root 2 over 2 plus b times y minus 0 plus c times z minus root 2 over 2 equals 0. That's what I know about my equation of my plane thus far, because I have a point on the plane. I just need the normal vector. Well, at this particular point, I need to evaluate what the normal vector is. So I need to actually go and figure out what's the normal vector at this point. But that means I need to know what u and v are, right? So I have to now figure out what's u and what's v that get me to this point on the original curve. Right? As I vary u and v around, I start drawing these things, right? I draw the whole surface. What does u and v have to be to get me to here? So where do you want to start? Yeah, I know that this right here has to turn into that, right? I know that cosine of u has to be root 2 over 2. Can you tell me what u has to be then? Where's cosine of u root 2 over 2? Pi over 4? U must be pi over 4. Anywhere else? 3 pi over 4? No, wait, not 3 pi over 4. It's over in the fourth quadrant, isn't it? Which is outside of my, right? Cosine is the x coordinate on the unit circle. That's only positive in the first and fourth quadrants. So pi over 4 is the only solution that lives in here. Okay, so we've nailed down what u is, right? Okay, let's look at this one right here. This has to be equal to that. So I must have that sine u times sine v must be 0. But I know what u is, right? U is pi over 4. What's sine of pi over 4? This is root 2 over 2. Sine v must be 0. Divide both sides out. You have sine of v must be 0. Where's sine 0? 0 and pi and 2 pi, right? So I have a couple of different options here. V could be 0 pi or, yeah, I'll say or 2 pi. Do you agree? That's not good enough. So we should be able to get it from this last one. How about this last one? Cosine v sine u must be root 2 over 2. We know what u is, right? U is pi over 4. Then this would be sine of pi over 4, which is root 2 over 2. So cosine v times root 2 over 2 must be root 2 over 2, which means cosine of v must be what? 1. Where's cosine 1? 0 and 2 pi? Okay, 0 and 2 pi. Well, if we plug in 0 or 2 pi, we're going to get the same point on the surface, right? See, over here it was 0, 2 pi, or pi, but pi could not be because it wouldn't satisfy the first one. What happens is if you keep drawing this, it's going to keep drawing the same sphere over and over. If I open this restriction up to like 0 to 4 pi, it's going to draw two spheres, one on top of the other one. So we have one point that's being overlapped here. So we can use 0 or 2 pi. It's going to give us the same result here for our normal vector. So what do y'all want to use, 0 or 2 pi? Use 0? Okay. All right, let's get this. The normal vector at this, u was pi over 4 and v was 0. I'll just put it up here. U was pi over 4, v was 0. And now we get the normal vector. The normal vector is, plugging in, what is this? U is pi over 4. So sine of pi over 4, root 2 over 2 squared, 2 over 4, which is half. So we have 1/2 times what's cosine of v. Cosine of 0 is 1. And then, OK, keep going. What's sine of 0? 0, that's all gone. What's cosine of u? What's cosine of pi over 4? Root 2 over 2. What's sine of pi over 4? Root 2 over 2. So root 2 over 2 times root 2 over 2? 1/2 again. There's our normal vector. Questions? You sure?
Yeah.
You got it?
I was just thinking, what if we had picked 2 pi and then I see that the middle one would be 0?
It would still be 0. Yeah, it wouldn't matter. All right, so the final answer for the equation of the plane that's tangent to that sphere at root 2 over 2, 0, root 2 over 2, at that point, is ABC, right? That's ABC? So A, x minus root 2 over 2, plus B, which is 0, times y minus 0, so it's not there, plus 1/2 z minus root 2 over 2 equals 0. There it is. Of course, you could clean it up. You can multiply both sides by 2. However you want. That's the equation of the plane. If we graph this plane, it should touch that sphere. At that point, it should be tangent to the sphere. Questions? What's remarkable about this is we should be able to do this for any surface, so long as you can cross the partials, right? If you can cross the partials, you're in business. Well, and if you can come up with the parametric representation of the surface, then you should be able to. Now, I think we're going to extend on this idea now a little bit more. We're going to talk now about surface area. We've been able to draw surfaces, right? Using this R of uv, we can draw a surface, three-dimensional space. We know that we can pick a point on it and we can find a tangent plane. But what if you want to know the area of a surface? Is there a way to do this? And we can, and here's the formula. It is the double integral over the region D, where D is going to be your restrictions on u and v. Now remember, you draw the surface with u and v, and you put restrictions on u and v. D is the domain restrictions on u and v. If you take a double integral over that of this dA. Now let me try and help you see where this comes from. Let's imagine we want to find the surface area of that particular surface, which in this case I made it a sphere so it's easy to see. If I wanted to find the surface area of this, I know I could draw it by changing my u and v, right? But let's just see, what would it take to figure out the area of that little infinitesimal little patch? Right? This is just a little infinitesimal patch on here. And I'll want to add up all the patches. right? If you add up all the patches, you get the total surface area. So one way I could do this is I could come down here like this, right? That's the tangent plane. Agreed? These two vectors are the whats? Those are your partials, right? Those are your partials. The area of this plane right here is the area of a parallelogram, isn't it? And do you remember the formula for the area of a parallelogram spanned by two vectors? It's the magnitude, right? The magnitude of the cross product. So you got to remember back from earlier classes that the magnitude of the cross products of two vectors is the area of the parallelogram. Refer to old notes. Two vectors, and you want to know the area of this. That's the cross product of the two vectors. So does it make sense to you that in order to find the surface area of this thing, what I should do is somehow scale that, I went a little too small. Scale that thing down. So in other words, instead of taking this entire vector, which let's say is r, the partial with respect to u, and let's say this one's the partial with respect to v, instead of taking the whole thing, maybe I need to scale it by something to make it shorter. How about we scale it by, I don't know, something like infinitesimal, like du, the little differential, and then do this one like dv, something like that. Then what we should get is an infinitesimal patch like this, and if we add them all up, then we would get the surface area. That's the idea behind this. And what would happen if you took this and you crossed it with this, the constants would pop out, and you would have du dv times each other. And guess what du dv is? It's dA, right? Because du dv, it doesn't matter which way I do it. That's what's basically happening here. Pretty awesome. I want us to find the surface area, and I want to change this. I don't want the unit sphere. That's too boring. Let's find the surface area of the sphere, radius. Let's go, so we don't confuse it with other r's, radius A. Now, if you look this up in a book, what's the formula for the the surface area of a sphere radius r? If you don't know it, don't worry about it. 4 pi r squared is the formula. The area of a sphere radius r is 4 pi r squared. So here's what our goal is. When we're done, we should get an answer of 4 pi a squared, right? That's what we should get if it matches up what you'd find in a book. All right, let's do it. You ready? Okay. I need to be able to draw the surface first. So how about we do it with this? R of uv equals, now let's use the same thing we used just a second ago, except it's not radius 1, right? It's radius A. So I'm going to go A, what was it, cosine v sine u, is that what I did? And then A sine v sine u, or sine u sine v. Then the last one, A cosine u. Are we on the same page? My u's between 0 and pi. My v's between 0 and 2 pi. We still good? If I'm going to use this formula, which is double integral over d of ru crossed rv dA, then I'm going to need to know some restrictions on d. Do I know the restrictions for d? Yes, here they are. So I'm good with the limits of integration. I'm going to have to figure out what the cross product of the partial derivatives is, and then take its magnitude. This is the part that's going to suck. All right, let's be careful and let's carefully go through this. What's the partial of r with respect to u? And now we have an a in here, so do you think we're going to get the same exact thing? Yeah, except what's the only difference? Think we're just going to have an a in there? Is it going to be an a squared? Uh-oh. Let's do this first partial. With respect to u, it would be a cosine v cosine u, a sine v cosine u, and then negative a sine u. Right? That's what that first one would be. Partial with respect to v would be negative a sine v sine u, a cosine v sine u, and 0, right? Cross them. What do we actually have in there when we do our little crosses here? We get 0 there, and then we get a squared cosine v sine squared u. What's the next one? How about this one? Will it be minus or plus? It's a plus, remember? Because it was that weird minus, but it was the middle one. So we'll get a squared sine v sine squared u. And then the last one's the ugly one. A squared cosine squared v cosine u sine u minus a squared, is it minus? Plus. Plus, sorry. Plus sine squared v cosine u sine u. So very similar to what we had, right? We weren't sure if it was going to be an a in there or an a squared, but it's a squared. Do you see that? This one becomes, just for the sake of time, this becomes, we can pull out an a squared cosine u sine u and then get Pythagorean. So we should get a squared cosine u sine u. So if you look back at the previous problem that we did, when we did this cross on the unit sphere, we just, all the a's, a squareds, they were all, a was 1, so we didn't see them. Okay, next. Magnitude. The magnitude of a vector is the square root of the square of each of the components. So we have to square each of these components, add them together, take the square root. And that may sound bad, but it's not going to be that bad. In fact, it's going to be great when it's all said and done. Things are going to go away. The magnitude of this will be square root of, okay, when I square this, I get a to the 4th cosine squared v sine to the 4th u. When I square this, I get plus a to the 4th sine squared v sine to the 4th u. And then when I square this, I get plus a to the 4th cosine squared u sine squared u. Anyone see it? Where's the Pythagorean?
It's a squared, a to the fourth, sine to the fourth, u.
Yeah, why don't we do this? Why don't we pull an a to the fourth out of everything and take it out of the root? An a to the fourth on the inside comes out as an a squared on the outside. Then, I'm ignoring those now, okay? On these two, I have sine to the fourth u, sine to the fourth u. Just pull that out of those two only. And I'll have sine to the fourth u cosine squared v plus sine squared v. And then over here I have plus cosine squared u sine squared u. Right? Which this turns into a 1. Pull out a, so with what's left, right, that's gone, pull out a sine squared u. You'd be left with sine squared u. So I'm pulling a sine squared out from this and from this. I'll be left with the sine squared here and left with the cosine squared here, which again becomes a 1, which gives me a squared square root of sine squared u, which is going to be a squared sine u. I don't need to put absolute value because u is between 0 and pi. Sine is always going to be, 0 to pi. Yeah, so it's always positive, so we're good. We don't need to worry about that. All right, that's it. Any questions on where I got any of that? Now we just integrate, right? Double integral. All right. So we're going to go double integral over d of a squared. So I'm going to pull that out because that's a constant, sine u dA, which in this case I know my restrictions, and they're both constants. So 0 to 2 pi, 0 to pi, sine u, I have to go d what here? With the order I chose here. d u dv. What's the antiderivative of sine of u with respect to u? Negative cosine of u, evaluated 0 and pi, dv. I know I'm going quick, but this should be trivial stuff at this point. Plug in pi, you get cosine of pi is -1, but then minus, so it's a 1. Minus, now plug in 0, cosine of 0 is 1, but minus, which is -1, but you're subtracting it, right? So that's really a 2, right? So you've got a 2 comes out 2a squared. It's looking promising, isn't it? Remember what we were trying to get to? Right? That's encouraging. I'm integrating, I pulled the 2 out, I pulled the a squared's already out there. This is just really like a 1 dv, right? The antiderivative of 1 with respect to v is v, evaluated 0 to pi, which is 2 pi. Hold on, what? Oh, it was 2 pi. I was about to have a little miniature panic attack there. Okay, 2 pi. I was like, where's the 4? Shit. Okay, so that's going to plug in 0, so we just get 4 a squared pi, or 4 pi a squared. Check. So we just verified the surface area formula for a sphere. We've done that before. We actually did it. You could do this using, in Cal 2, revolving, like the first quadrant, just take this first quadrant, that part of the circle, revolving it around the x-axis and using the surface area formula. But this is verifying it using a vector function to draw the surface. This is more powerful because this will work for more complicated surfaces. But it's nice that it verifies, right? All right, sometimes, we've got about 9 minutes left. Sometimes if we're lucky, all right, we can actually have a function, a surface, that's the good old-fashioned z equals f of x, y. The first type of function that we dealt with when we were drawing surfaces. You know, a good old-fashioned sheet of paper, the domain is on the ground, right? Not like a sphere where it wraps around itself. You can't look at z as being a function of x and y. If that's the case, all right, then you can basically let your u be x, let your v be y, all right? And then, so it's like this. In your vector curve, you're doing this is x, this is y, and then this is actually the function of x and y. So like if this were u and this were v, this would be some function of u and v. Then if you go through and do the cross product of the partials, it will always turn out to be this. Now I don't do it, I'm not going to do it. I say y here. Y will, you would have to take this and take the partial with respect to x. What would the partial of this with respect to x be? 1, 0, partial of f with respect to x, right? What would the partial of this with respect to y be? 0, 1, partial of f with respect to y. Now if we cross these, lots of things are going to go away. We're going to get 1s in there. And then if you take the magnitude, square root of all that, you will get this formula. And it's super clean and quick and easy to use, all right? I'm going to give you an example of this. So it makes our surface area formula real easy to compute. So here's an example of that. We have, yeah, it looks bad. You have a surface, right? Find the surface area of the part of the paraboloid z equals y squared minus x squared, which lies between these two cylinders. It's hard to see it here. It's this orange looking thing. I'm going to pull all the other junk out of there. This is it right here. What we've done, though, is we've taken these cylinders and we've cut it. So it's like this sheet of paper that on one side it goes down, the other side it goes up, so there's like a saddle point in the middle. And what we've done is we've come in with two cylinders and chopped it, and then a smaller cylinder and chopped it. And we're looking at the surface in between those two. So we chopped it here from the top like this. And when we chop it, we just get that. And we want to know its surface area. So that's a pretty complicated looking question, right? Without anything that we have today, that would be a tough question. So when we look at it, say, okay, well, how do we draw this surface? How do we draw this surface? Well, it's here. This is the surface, right? We've got some restrictions, but that's basically the surface. So I know that the z there is a function of x and y. And that makes me happy because if z is strictly a function of x and y, then I know that the magnitude of the partial with respect to x crossed with the partial with respect to y should be equal to the square root of 1 plus, I'm going to write it this way, partial of f with respect to x squared plus partial of f with respect to y squared, which was the formula I gave you on the previous page. Now, for us, what would that be? I should have written what the function is. What is the function? Sorry. Y squared minus x squared. So this should just turn into square root of 1 plus 4x squared plus 4y squared, right? That's what the partials are. Well, the partial is what? Partial with respect to x is negative 2x, but then you square it, so 4x squared. Partial with respect to y is 2y, but then you square it, you get 4y squared, right? So that's what I would have to integrate. Isn't that a lot easier than having to do the partials, then the cross product, then the magnitude? Okay, it only works so if your surface is a function of two variables explicitly. All right, so let me get to where I want to set up the double. So I'm at this point right here. I'm trying to set up the double integral over some region D of this with respect to area. Now, I need to be able to come up with the appropriate restrictions on x and y so that I get just that part that got chopped off by the cylinders. How do you reckon we do that? Go to cylindrical coordinates or polar conversion. Right? Think about on that picture, on this picture, if I'm going to try and get restrictions on x and y, I need to look at it from the top and say, hey, what type of region is that on the ground? That's a polar region, isn't it? So I'm going to take this whole problem and convert it to a polar problem now. So what would my polar restrictions be to draw that thing? Do I have I have the cylinders up there. Can you tell me what the radii of those cylinders are? 1 and 3. So we want to restrict our x and our y into this region, so we switch to polar. So I'm going to let my r go between 1 and 3. I'm going to let my theta go between 0 and 2 pi. And now I just set it all up, right? This double integral. This doesn't matter, right? Because they're both constants. Square root of 1 plus 4r squared, right? Factor out a 4 from each of those two, and you're left with x squared plus y squared, which is r squared. So we have to see that to make our lives easier. You could replace that with r cosine theta, r sine theta, then do all the squaring in Pythagorean, but it's much cleaner if you just notice it. And then times r, yes, you cannot forget the mighty r that comes in every time you do polar. And that actually saves us a little bit, doesn't it? dr d theta. And then why did I do 1 to 1? I don't know. 1 to 1. And then at that point, you just go. I'll tell you what the answer is, okay? I don't have time to work this out. You should get at the end of this equals pi over 6 times 37 to the 3 halves minus 5 to the 3 halves, whatever that number is. That would be the surface area of that region between those two cylinders for that surface. Now, I had planned on working a few more problems here. I have not had a chance to get into to do the homework solutions for this. All right, so I don't have the homework answers on video for these. But here's the homework assignment. I don't know when I'll be able to get those videos up. Hopefully in the next day or two. Maybe tomorrow morning if I'm lucky. So I know we're out of time, but just to give you an idea, we're done with 13.7, 6. 13.7 is probably going to take us all of next class and probably part of next week's class to get through 13.7. 13.7 is the last big, heavy section. 13.8 and 13.9 are 13.9 will take about 15 minutes. It's just really one formula and it's super clean and nice. 13.8, maybe 30, 45 minutes. So we will spend every class from here to the end talking new material. Question?
This isn't on the mini exam, right?
I don't believe this is on the mini exam. Nope. No, yeah. But we will finish this book. We are going to finish the book. All right? We will do that. Do your homework. Keep up, okay?
No, I took
Roy said it's just computation, right, for us?
Yeah, the rest of what we're doing, what we're gonna be doing.